Now it's recording. Thank you, Pat. All right. So I cleared all my lists, and I'm going to go to my lists and put the month in list 1 and the average temperature in list 2. Let me slide this. Okay. So 1 through 12. And then my average temps in list 2. Now, the first time we go through this set of data, we're going to find a transformed sine function, and then we're going to do the very same thing using the cosine function. You can use either one. You don't have to do both, but you can use either one to find a function that describes the pattern of this cyclical data. Okay? Alexa. You're good? Okay. All right, so the first thing we want to do is take a look at this data and just see if it does in fact look like it might be the sine, a version of the sine or cosine function. So I'm going to go to my stat plot, second y equals, and I'm going to go to plot 1 by hitting enter. And I want to make sure that it's on, and if it's not, I hit enter on the on, and that my scatter plot type is selected, that's the first type, and that my x list is L1 and that my y list is L2. Okay? Then I'm going to go to y equals and just make sure I don't have anything in there from another class, and I don't. So I'm going to, how do I get my window to fit a scatter plot? Zoom 9. Okay. Oh, look at that. Does that look like it could be a part of the sine or cosine function? It does. Okay. Now, what I want to recognize is that I see that this function is repeating itself. It looks like I'm starting at the bottom, or at the valley of the function, and then I'm reaching one of my bumps, as I call them, and then back down to the valley. And then I think that's going to repeat itself thereafter, right? So this might be considered one cycle of this function, okay? And therefore, good job, Aisha. Therefore, it represents one period, okay? Now, in order for us to be able to determine the transformation of the sine function, we need to figure out first what, the scale change or the translation rule, which always comes first. Yeah, the scale change, because any multiplication or division always comes before any addition or subtraction. So, to get a scale change, I know that my general rule basically is going to be I need to figure out what I'm going to need to do to the x coordinate and what I'm going to need to do to the y coordinate. So I need to find the a value and I need to find the b value, don't I? Okay? Now, the b is called what in the graph? It's the amplitude. What does amplitude represent on the graph? What about the highest point? Nope. It has to do with looking at the highest and the lowest and then cutting it in half. You're right. So what we basically need to do is determine what's this high point, what's this low point. Well, that's obvious right in the data, isn't it? Okay? So our highest temperature was what? 73.2, and our lowest temperature was 21. So the distance from highest to lowest can be determined by subtracting those. And then like Alex was remembering, amplitude is half of that distance. So I'm going to need to multiply that answer by 1/2. Okay? So I'm going to do that. I'm going to take 73.2 minus 21, get an answer, and then cut that in half. So I find in this case an approximation of my amplitude would be about 26.1 degrees. Make sense? Okay. So I've got my B value. Now, what does A have to do with in the function? What does A affect? The period. And we know we do what with A to get the period of a function? Times it by 2 pi. Okay, so we'll do this in radians since that's what we've been spending the majority of our time with our graphs in. So I know that I can find period by taking 2 pi A, and of course if A is negative, I ignore the negative, and that should equal the period. Well, the period is how often this cyclical data repeats itself. And how often do these temperatures repeat themselves? Every 12 months. So 2 pi A has to equal 12. Can I solve this for A? Okay. So I know that 2 pi A is equal to 12, and so I need to do what, Alex? You got it. So 12 divided by 2, of course, is 6. So I end up with A equal to 6 over pi. Okay? So I determine the amplitude just by taking half of the highest minus lowest. And then I determine the period based upon how often the pattern of temperatures repeat themselves, which is every 12 months in this case. And then set that equal to 2 pi A and solve for A. Does that part make sense to everybody? Okay, so my scale change rule would be every point xy is going to map onto ax, which we now know A is 6 over pi, by, which we now know B is 26.1. Okay? Any questions so far? All right. Now, we're going to use the sine function here first. So when I go to determine my translation, I need to think about a point that I know is on the sine function. That's easily identifiable. Now, when I say easily identifiable, I typically either pick a point that I know is a bump, or I pick a point that I know is a valley of the sine function. So can you think of, say, a bump, the coordinates of a bump on the sine function? When does sine reach its highest value? No, the sine function itself. Pi over 2, right? Pi over 2 is when sine is equal to 1. Okay, so I know that there is a point on the parent function at pi over 2, 1. Right? Now, if I perform the scale change on that point, then that means I need to multiply my pi over 2 by 6 over pi, and I need to multiply my y, in this case 1, by 26.1. So all I'm doing is I'm transforming that bump just with the scale function. Okay? Ooh, that's better. It's a little bit too bright though, isn't it? Okay. Now, if I go ahead and do that multiplication, these pi's cancel, and 6 over 2 is 3, and 26.1 times 1 is 26.1. Okay? But in my data, is there a bump at month 3 with a height of a temperature of 26.1? No. Where is the bump in my data? Yes, it is month 7 when the temperature reached a highest point of 73.2 degrees. Okay?
I'm confused why we multiply pi over 2 and 1 by the coordinates.
because that was my scale change rule that I just came up with.
Oh, you're trying to find.
I'm applying my scale change rule to a point on the parent function.
Gotcha.
Got it? Okay, anything else before we move on? Okay, so after doing the scale change, we didn't land on the bump. Our bump in our data is actually at month 7 when the temperature is 73.2. So now the question is then, how much more do I need to move to get from 3 to 7? Ah, I have to add 4 to the x-coordinate, don't I? How much more do I need to move to get from 26.1 to 73.2?
47.1.
Okay, so how'd you get that, Kyle?
I did 73.2 minus 26.1.
You got it. So it was 47.1, you said?
Yeah.
Okay. So basically what we've determined is after the scale change, our coordinate would be at month 3 with a temperature, high temperature of 26.1 degrees. But that's not what we saw in our data. In our data, we saw that it wasn't until month 7 that we reached a high point when that temperature reached 73.2 degrees. So there was more shifting that had to go on. I have to shift an additional 4 places to the right to get from 3 to 7, and I had to shift an additional 47.1 up to get from 26.1 to 73.2. Make sense? That's my translation rule. Okay? So my vertical shift is positive 47.1, and my phase shift is my positive 4. Okay? So now the rule for my translation is that every point xy after performing the scale change is going to land on x plus 4, y plus 47.1. So we've got both of our rules. And now the question is, can we use them to write an equation that will model this data? That's the big question. And we know that whatever you do in the rule, what do you do in the equation? Okay, so I'm basically starting with my sine function. Y equals the sine of x. Leaving a little space there. Okay? Now, I'm going to start with my scale change rule. In my scale change rule, x is multiplied by 6 over pi. What will x be multiplied by in the equation?
Pi over 6.
Yeah, that's like dividing by 6 over pi. So there's going to be a pi over 6 out here. And it's what I factored out. Remember when we learned to combine scale changes and phase shifts and vertical shifts? You had to factor out that number in front of the x. So that's going to go out in front of the parentheses. Okay? In my scale change rule, y was multiplied by 26.1. So y will be divided by, but if I want to be able to put this in my calculator to see how well it fits, what would I put out in front? Yeah, the other side is going to be multiplied by 26.1. So I've got 26.1 times the sine of pi over 6 times some quantity that has x in it, right? That makes sense so far? Okay, hang on, I think I'm a little blurry. Do you think I'm a little blurry? Is that better? Worse? That's better, right? Okay, so now I want to apply my translation. In my translation rule, I added 4 to the x. What am I going to do in the equation? Subtract 4. And in my translation, I added 47.1 to the y, so I would subtract it from the y here, or stick it on the end and it would be plus, wouldn't it? Which I'm going to do because I want to be able to put this in my calculator. Okay? Any questions on how we came up with that equation? Right, now we have to be very clear in the way we communicate with our calculators at this point. I want my calculator to take the sine of that whole thing right there, don't I? So I'm going to need to put that in parentheses. This would only be important when I want to graph it with the data. So I'm letting my calculator, don't just take the sine of pi over 6. Take the sine of that whole thing, pi over 6 times the quantity x minus 4. Okay? The other thing I need to be clear about in my calculator is I got to let it know what units I'm using. And I'm using what units here? Radians. Okay, so I'm going to first go to my mode, and I'm going to make sure I'm in radian mode, since I use pi's. Okay? Then I'm going to go to y equals, and I'm going to carefully enter this equation. Okay? So I've got 26.1 times sine of the, and it automatically gives you the open parentheses. So I'm going to put my pi divided by 6. And now I need another open parentheses. X minus 4. And I've got to close both parentheses. Sorry about my little glitch in my screen. Okay? And then I have a plus 47.1. Everybody good with that? Now our window's already set to fit the data, so it should be set to fit the equation as well, if we've done this correctly. So let's graph. See how we did. Ooh, are we good or what? Cool. So now we could use our model to make some predictions for like what the temperature might be, say, during month 11, day 4. Well, that'd be an x of 11 plus 4 30ths, right? Because the month of November has 30 days, right? So we could use our equation to make some predictions for temperatures on any particular day during the course of the year. Kind of cool, eh? Now, yay! What would be different if we used cosine? What would be different if we used cosine? Is the amplitude different? Is the period different? No. Is the phase shift and vertical shift going to be different? Because the bump's in a different place, isn't it, with the cosine function? Okay, but before we do that, any questions on what we did? Okay, so on the other side, you'll notice I've given you a place to do something similar with our cosine function, okay? So we still have the same scale change rule because you told me period and amplitude are still the same. So I've got every point xy is going to map onto 6 over pi times x, and then 26.1 times y. Okay? We've got to find our translation. So we got to think, do you want to use the bump again? Okay? Where is there a bump on the cosine function? 0, 1, right? We see that first bump right on the y-axis. Okay. So I've got the point 0, 1, and I'm going to perform my scale change. 0 times 6 over pi will be what? 0. Thank you. And 1 times 26.1 will be what? 26.1. Okay. But there is not a bump at 0, 26.1, but rather at 7, 73.2. Same bump, right? So what's my phase shift? What do I have to do to x? Anybody? What's that? 7. Add 7. What's my vertical shift? Same amount, right? 73.2 minus 26.1 is a vertical shift of 47.1. So my phase shift changed but my vertical shift did not. Okay? So when I go to write my vertical shift, it's 47.1 in a positive direction. And my phase shift is 7 in a positive direction. So what's my rule going to look like? What's XY going to map onto? Anybody? Thank you. And? You agree with Sydney? All right, now everybody on your own, without the help of a neighbor, see if you can write the equation for this transformed cosine function. It's opposite operation. Why don't you do this? When you get it, be sure you give your neighbor time to get it as well, but then turn to your neighbor and see if you guys agree. Agree, but be sure to give them the time to figure it out on their own before you come to it. Are you in agreement?
Yeah.
Anybody in disagreement with their neighbor? All right, let's try it then. Okay, you got y is equal to 26.1 cosine of the quantity pi over 6 times the quantity x minus 7, close, close, and then plus your 47.1, right? Is that what you got? Okay, so let's just go back to y equals. And what we need to change here is our sine to cosine. And we need to change our phase shift from x minus 4 to x minus 7. Everything else is okay, right? Let's hit graph. It's magic. Love it. Love it. Isn't it fun to see it all come together? Come on, you guys. I do too, it is. And can you think of other things in our world that might be very cyclical? Roller coasters. Yeah, I suppose we could collect data and determine where the car is after certain periods of time with respect to the bumps on the roller coasters. Can you think of anything else? Cyclical? Weather is cyclical. Roller coasters are cyclical. Pardon me? Rainfall. Maybe if we looked at some rainfall collect data over the course of a year's time, maybe, we might see that it does in fact have times when there's a very large amount of rain and other times when there's not so large.
No, that's
Okay. Well, the problem that I have you doing for homework here today is number 10, but I've got it mapped out similar to the way I have it mapped out here, but let me pause my recording.